Good.
Sorry. Okay, I'm Mike W8PQ. I am a dues-paying member. I don't get to come to too many meetings, maybe once a year. Anyway, happy to do this. It's a presentation that I did a few years ago with a ham buddy of mine in another state, and I thought it was a good follow-up to Chris's nice presentation from last month, and we'll look at some more things about antennas. Amateur radio means someone that loves radio, basically. Before there were professionals, there were only amateurs, because there were no professionals. There were scientists trying to figure out how physics works, and the whole idea of radio developed, and here we are today. But we've gotten to the point where the science is so sophisticated now, there's not much anymore that we can do to have fun creating it. But antennas are something that you can do. Anybody can make their own antenna, no matter how much you spend on a fancy rig. You can make your own antennas. And antenna modeling gives you the mathematical assistance of a computer to look at all the kinds of what-ifs you might do. And in the industry, whether you're building cars or whatever, you don't have model shops so much anymore. You have virtual prototyping. So what you do is in the computer, you virtually create a model of the thing that you want to make and see how it performs before you have to build it. And you can do this over and over again, reiterate it over and over again until you get it the way you want it, and try all kinds of different things. So antenna modeling is basically about applying arithmetic or mathematics to the concepts that make an antenna and come up with how this thing will behave based on the physics that makes it happen. Most people are familiar with the mathematical formula for the area of, say, a rectangle. You have height times width, and you come up with the area. That's mathematics, okay? If it's 3 feet this way and 5 feet this way, you have 15 square feet, right? That's a simple formula. Many of you, if you come from a technical background, and a lot of people in ham radio do, you understand Ohm's law. So you have E equals IR, you can multiply the current times the resistance, come up with the voltage, or any relationship there by moving the equation around. Okay, so, but basically what you have is some kind of energy going down a wire or metal surface, and that because of that energy is existing in that environment, it's going to create these electromagnetic waves that make radio possible. All right, so Chris showed some antennas last week, looked at the J-pole, or last month we looked at the J-pole and stuff like that. I have some things here that came from an antenna that I thought was very successful, came right out of the handbook, and so we got some examples here. Some type of plastic way to mount a connector, and then you bring out the two sides of your antenna. You can mount it on a pole or on a tree or whatever you want to do, and you can have different kinds of coils on it, but you're going to get the wire out in space so that you can send electromagnetic waves out and receive electromagnetic waves. And whenever we talk about antennas, it's good to know that antennas are completely reciprocal when it comes to transmit and receive. The behavior is identical, whether it's a transmit antenna or receive antenna. So if you know how it's going to perform as a transmit antenna, it's going to perform for the same frequencies, with the same kind of gain pattern, etc., for the receive antenna. So some of the things that I have here are the basic components that make up an antenna. So these are basic PVC couplings. Probably seen something like that before. You can get these by using matching vitamin bottles. These are great because they're just the right size for most of the things you might want to do in an antenna, and you can drill holes in the ends and you can put these concepts together. I chose to do it this way. So this is a coil, and this is the capacitor that came off of my trap antenna that I used a little bit west of Chicago, and I used that for about 10 years and worked, worked around the world. I didn't try to get VXCC or anything like that, but this is basically a capacitor. If you put a capacitor and a coil together, you've got a resonant circuit, right? So basically you mount them like this so that you've got one plate of the capacitor on each end of the coil, and then your antenna goes from here to here. So there's some things here you can look at to see with these. You can pass them around and then bring them back. That's what it looks like. Well, it doesn't really look like that when it's done. It really looks like, it looks more like this when it's done. So I have the two places I can hook it up. I got nuts and bolts on there, fixed in place by electrical tape. But essentially what it is two separate surfaces that can hold an electric charge, okay? Separated by some kind of dielectric. And this is all stuff you can get in the hardware store. This is 3/4 OD by 5/8 ID, and I think it's something that I used on some of these. You can also use the larger sizes, but this is basically a vinyl. The vinyl has a dielectric constant of about 2.8 to 3, so you can calculate this very easily. And what happens is if you have that material and you put it on the inner piece of metal and the outer piece of metal goes over it, there's no DC connection between these two, so it can only be passed through by changing fields, electric fields. And that's how a capacitor works. Now, if you study it in a book, you'll see that a capacitor has these square plates, one this way and one this way, and then you have voltage here and the opposite voltage on here, and it causes an electric field in between. But you can do it easily with these, and you can find these for sale like this. People have made these for years like that. They handle pretty high voltages, but you can use regular capacitors that you would buy at Radio Shack. So by the time you put the connectors on each end, it's going to look like that. And guess what? I've got a variable capacitor if I found a way to do that too. So take a look at that, pass that around. You can pass the coils too for that matter. But I've got these here. I would like to try to put a couple of these together and make an antenna. And we're going to test it. We've got a antenna analyzer over here. I also got my grid dip oscillator. We can use that. Let me pass this one from this end too. How many of you ever made these? Yeah. So I just, I'm the kind of guy that likes to go to the hardware store and find something and make everything from that. So I've got all kinds of different kind of antennas that I've made that way. If we want to check out the capacitance of one of those things and the inductors, I brought my bridge with me so we can do that, and the antenna analyzer. So this is a great resource. The two basic things that you're passing around are inductance and capacitance. Those are the two physical parameters that are necessary to make AC work. Those are the two parameters. So just about everything has either an inductive or a capacitive property. Some have both, like if you put a trap together, and actually because of parasitics, most everything has both because of parasitics. So even a coil like this, because there's a different voltage between each winding of the coil, there's actually a capacitance between there, even though it's an inductor. But that's for something else. So if you go into the handbook, you'll see that this describes physically what a capacitor is like, and it even shows us the formula for capacitance. And you can use this formula of capacitance, apply it to these so that you can calculate what size you need of those copper tubes. Then over here we have inductance. This is a standard solenoid inductor, which is this. We have a cylindrical shape that inductor goes around, and if you know the length and you know the diameter and you know how many turns you have over that length, you can calculate what that inductance is. And so I just didn't pick these sizes because I thought they were nice sizes. I looked at what the handbook says they need to be, and then I backed into that. So this is one way of doing that. If we look at an antenna, you can have one antenna for every frequency if you want. You can, but most of us like to be able to move from band to band and change around, which is why I like trap antennas. It's more ideal if you can have a perfectly tuned resonant antenna for every single frequency you're going to operate. And since if you can't have that, you'd like to have some kind of tuning mechanism at the feed point of the antenna, not at your transmitter, but all the way down the cable at the end where it attaches to the antenna. If you could tune it there to match it to the cable, that would be your best bet. But most of us don't have that luxury, so we tune back at the antenna, back at the transmitter output, so we can keep the reflected energy, because our antennas are not resonant. We want to keep that reflected energy from getting into our transmitter and ruining it. But that's just something to look at another subject. So an antenna is going to be basically the dipole antenna. It's going to have a feed point in the middle, and it's going to have wires going out to each side. So you're going to have a dipole. Basically, plus on one side and minus on the other side, if you will. So you have plus current going this way and minus current coming this way, but they're actually both in the same direction. That's another story. So this shows you what a dipole antenna is, and then this shows you the basic algebraic form of the equation for a dipole antenna. It's corrected here for real world, so the formula is basically a half-wave dipole antenna, which is what these are, where you go up to a feed point with your coax or your ladder line or whatever, and then you go this way to one insulator and this way to the other. That's your dipole. Ideally, it should be resonant to be a half wavelength of the frequency you're working on. From that end to that end should be a half wavelength. And you can calculate that as 468 over FM megahertz. So if you have a 4 megahertz, if you work in Mars and you're running 4 megahertz, for instance, that would be a 117-foot antenna. If you're working something like 3.9 to 3.8 megahertz in the regular hand band, you can be down around 130 feet for your dipole antenna. So you can see that these are formulas, but you can put all this stuff into the computer and go from there. What I do when I'm working on Windows wants to wake up. Oh, that's why I can't see it. Okay. So what I do is just take an Excel spreadsheet and I put those formulas that I showed you in the book, the one for capacitance and the one for inductance, and I put them in the book, and I can calculate any number of things that I want to try on here. And I usually do that so I can have the right values to plug into the antenna modeling program if I'm making a trap antenna, for instance. You don't have to make a trap antenna, I just show that because it's one of my favorite kinds. Mathematical formulas that represent these different properties. I have a formula for capacitance typed in here, and I just take a couple of these columns, and I have C for capacitance, the diameter of my little tubular pieces of copper, and I have the thickness of my dielectric. I have the dielectric property, which, like I said before, was like from 2.7 to 3 for the dielectric constant. And then I can calculate the sizes of the amount of capacitance that I'm going to have for the particular diameter I have and for the length of my capacitor. So if I want 16 picofarad, I would have a little over 2/3 of an inch diameter and a thickness of 1.13, thickness of 0.13, length of 1.38 inches. So that's just for capacity. And here's the formula for inductance that I showed you in here for a solenoid-shaped coil, as opposed to a toroid or something. And I can figure out the amount of those in microhenries. So something like 44 or 25 microhenries. There's a really good multi-band trap antenna that's been in the manual for 30, 40 years. This one is by W8NX. This one has resonances on the 80 meter band, the 40 meter band, 17 meter, and 12 meter. The ones that I built in the past had 80, 40, 20, 15, and 10, this 5-bander here. Something like that is very handy because that's most of the bands that we want to be on when we're on HF, unless you're doing some special stuff. So anyway, just wanted to show you that. You can, just like anybody, you can go to a manual like this, take those mathematical formulas, put them into your spreadsheet, calculate the values that you want. And if you don't know how to do that, I'd be happy to send you a spreadsheet. So anyway, I'm going to get those out of the way for a moment. And so what did we cover? We covered a little bit about the dipole antenna. And let me say this while I'm saying the word dipole. A lot of times you'll see a vertical antenna, which is just an element sticking up in the air. It might have some radials, but you'll see a antenna that's sticking out of your HT. And it looks like it's a monopole duct or something like that. I was working for 6 years with a PhD in higher energy physics as my application engineer, selling electromagnetic simulation tools for industry. He made this statement a couple of times to customers. He says, every antenna is a dipole. Every antenna is a dipole. So no matter what anybody else says, there has to be two halves of the antenna. Sometimes the question is, what is the other half? So if you put a mag mount on top of your car body is the other half of your dipole. But you have a dipole antenna. So that being said, we'll look at some things here, but I'm going to stick mostly with the dipole antenna. We looked at the different properties of an antenna. An antenna can be itself either capacitive or inductive at the frequency that you're at. We would like it to be resonant. And one other thing I meant to say, how many people have ever taken a rope and held onto it one end and then flicked it like this and you saw a wave go on the rope? Okay? And if you could get it just right, the wave would stay there. All right? Do we have any markers for the board? Over there, I wonder. Well, so the same thing happens with an antenna. When people talk about standing waves, they are not kidding. The antenna, when it's resonant at the energy that's exciting the antenna, that standing wave is a real thing. It's really happening. It looks like nothing's moving. But the thing that maintains it is the energy that's moving into it at the perfect frequency to make it look like the fields are standing still. And the energy that comes in obviously has to go someplace. And that ends up going to the person who's receiving your signal. So you will see an antenna and they'll say, okay, if this is my dipole, this is one half, this is the center for feeding it, okay? This is one half, this is the other. You will see current, really high current in the middle when you feed that dipole, and at the ends, the current goes to zero because there's no other place for the electrons to go. So your current is maximum in the middle, and it tapers off to zero at the ends, and you'll see that in the presentation, okay? Sometimes you'll look at that as being, if you look at the voltage part, the voltage will be maximum at the other end, right? And minimum at the middle, the current's maximum in the middle. So, and it actually will look kind of sinusoidal, going to the peak of the sine wave and coming down to zero in the middle. But anyway, those are things that you can look at later. But standing waves are the best way to get the most energy out of your antenna. And that's what we want to do, is the most effective, most efficient antennas that we can, right? So let's look at how we do this. No, I guess I'm okay. Well, but thanks. So, give some credit to my friend and colleague George Volman, who I met out in South Dakota, and he's now working down at Naval Surface Warfare Center in Crane, Indiana. And we were both members of the Ham Club there, and we happened to work with the same company. And his wife's actually from Grosse Pointe, and she's a sailor, so she can't be all bad. And she plays the banjo, so. But anyway, thanks to George Volman. So let's look at how this works. Antenna modeling is a computer automated calculation. We've looked at some of the calculations, just a few of the calculations that belong to figuring out what an antenna should be. We've looked at how to calculate capacitance and inductance on lumped elements that are in the antenna. But the antenna actually has capacitance and inductance across the whole antenna. We've looked at how long an antenna should be for a particular frequency, but so there are these parameters, and the computer automates the calculation of those factors. So in order to be able to calculate that in the computer, you have to tell the computer what the antenna is. So it's a structure, and it's a structure in space, whether it's a thing like this, or whether it's a rubber duck, or whether it's a mag mount antenna on your car, or whether it's the fin sticking down from an aircraft fuselage. An antenna has a structure, and we want to describe that structure and give it the proper dimensions so the computer knows what to calculate. Also, where is the energy applied and under what conditions? We talked about these inductive and capacitance loads like I passed around. So we're going to look at its behavior. Remember before I said this was virtual prototyping, so this is a simulated performance of what would happen in the real world. So depending on how good your programs are, would depend on how well they're going to match the real world. And that's why I brought these components, so we could put a quick one together and try it. So, a lot of you have probably seen pictures of the automotive industry when they show the cars all divided up into little pieces and stuff. You don't see all the pieces here, but what you actually see is the simulation of the wave solutions for this antenna operating on this particular aircraft. But people design and optimize these using programs. So we talk about the description of the antenna, the structure, the feed point, how the energy is applied, the elements and things like that. Here's an example of someone modeling this monopole antenna to go on your HT, for instance. This is a delta antenna. So if you look at anybody who's gone to school and had math, you had Y and X were your basic dimensions on your Cartesian coordinates. But if you come out of the page or into the page, that's the Z direction. Of course, we can orient that any way we want to. And the way we look at these antennas is we have X and Y on the ground, and we have Z going up. So just so you know, that's the convention here, okay? So if I see this X and Y, that means this would be the ground dimensions if I were standing here or wherever. And then how high is the Z direction. Now that way I can describe this structure. This looks like an inverted V, but it also has a wire this way and it's fed right here. And that happens to be a delta loop. Now the program that we're going to look at today was written by, I can't remember the call sign. And it'll be on here in a second, but a gentleman from Tektronix. I had the pleasure of working for Tektronix for 7 years, working with oscilloscopes and spectrum analyzers and all kinds of neat stuff. And just happens that he was one of the people out there in the early days that maybe even met him one time when I went out to the plant. But he was one of the early guys there. And he's the guy who developed this program that we're able to use virtually for free. And for a while, for several years, there was a version of it that was made and distributed by ARRL. That isn't happening anymore, but you can get the demo version of his product, or you can buy the full product for like $100 or so bucks, and it's really not that bad if you really want to do a lot of antenna modeling. But it was based on this NEC, numerical electromagnetics code, that was, I think, basically done for the military at some point, but it's able to calculate different parts, as you'll see here coming up shortly, and that's what this program we're looking at today is based on, is NEC. This talks about integral calculus and boundary elements and things like that, and if you're not a mathematician, you probably don't care. Everything that goes on in electromagnetics is based on Maxwell's equations, and you can look at the history of Maxwell and what these different equations are, but you can see the first one is all about the E field, the second one is all about B, the magnetic field, and then in Faraday's law of induction here, and Ampere's law. And they involve some math that I learned a long time ago and I have since forgotten, probably 25 or 30 years ago. So, now, I did work for this company, and that was their business, was doing these programs in finite element analysis that were used by the military and everyone else. And what happened was, as you may realize, Ohm's law is nice, but if you're going to develop a transceiver for sending Ethernet back and forth, and you're going to sell a chip that you're going to put on your circuit board, and it says this thing needs to have 50 ohms from each side of the serial data line say to ground. So you got 100 ohms total, you got 50 ohms from each side to ground, and that's real nice. So you put a 50 ohm termination resistor on there, and it works fine as long as you're down around 1 to 10 megahertz. And then when you start getting up higher, all bets are off. And so people have to actually model the circuit boards, the connectors, the vias on the board, they have to model them and shape them such that they're going to be 50 ohms when this particular frequency of energy hits those structures. I had one, Seagate used to be a customer of mine in the Twin Cities. And you look at the arm of the disk drive with the pickup on it, and it's got these funny shapes and everything going on in order to maintain the right impedance across the whole arm so you can get to the circuit board. And these things are done by taking the device and splitting it up into solid forms. And they're all triangular, so a solid triangle becomes a pyramid or a four-sided model here. So you got four sides. And what happens is they can take Maxwell's equations and solve them on each side and at each of the vertices, or the points where they come together if you don't know what a vertex is. You can solve Maxwell's equations there, and then you can sum up all the fields. So many of you probably learned that in school, when I have electricity going down the wire, if it's positive over here, so the convention is current goes that way, I put my thumb along the line, and then my magnetic field is out here, or if I go into this direction, current. Well, you can take that in every little piece, solving it with the most sophisticated equations, and all these fields then get added up, so you can see what the performance is. And with the computers we have today, you can take that to, you can see how they take the same shape and iteratively solve it until you get the finest detail you can. There was one, so I was basically doing the sales, and my application engineer with a PhD was doing the real work of proving to people that this does what it does. And this is a very successful business. I haven't been in this business since 2006. So it's nothing new by any means, and it's the way people do everything now. But there was this one company that had a filter with all these cylinders drilled into them, and then they had tuning slugs for them, right? And they're trying to say, your simulation doesn't work, we can't get the same performance out of the prototype that we built that your thing predicts. So your stuff is no good, and we're not going to pay $50,000 a crack to buy your software. And they went back and forth trying to make the models work. And so as the story goes, this is how critical it is. The application engineers convinced the company to let them see the model, and they looked at the model and they found a scratch in one of the cylinders. And they modeled the scratch in the geometry, and it came out right. And I had people, there's defense work that goes on at Mayo Clinic that's got nothing to do with health. And these people, some of the engineers over there, and that was another customer of mine, they were doing 30, 40 layer packages for a grid array IC to go on in ceramic, not phenolic. And because of the high speeds that they're working with, well, they have to model that whole package. And what is it? 400, 500 pins? I don't know. And they're modeling the whole thing to get the performance right. It's very critical. But ours is simple. We just have dipoles. So but this is the state of the art of how this works. So when you take a dipole, they don't have to really do it in 3D. They just have to do it in 2D. And what happens is, obviously, energy comes up the middle, and then it, positive energy is going this way, and negative energy is coming back down the coax, theoretically, right? The shield. And if you were to split that up in little bitty sections and then calculate those fields in each segment, then you can put together the whole thing. So what happens is you'll get results that you can see like this. Here's your SWR over a range of frequencies. And this one's going from, I really can't read it here, 5 something to 5 something maybe, I don't know. And we got a Smith chart, but mostly we're going to be concerned with the azimuth and elevation charts, because we want to tell do we have gain in a particular direction that we're looking for? Or do we want to have an omnidirectional antenna? And how is it, what's its angle of takeoff? You know, can we use it for DX, or can we only use it for like near vertical incident skywave for local communications? So this is something a little more common. You see our X, Y, and Z here, and you'll see the shape of the energy coming off the antenna. And you can see the pattern has a little bit of gain in this direction. It's still pretty omnidirectional, but a little bit of gain in this direction. And it shows your SWR over a particular band here. This is an example of one of the things they do in industry. They have specific absorption rate for the energy that your head absorbs when you have an antenna. So people that are doing that commercially have to take that in consideration. They have government regulations on that. Now, this is a critical part of it, okay? Where are our points in the frequency range that we're looking at that are going to be resonant enough to give us a low enough SWR, okay? In other words, if I use this antenna, what's its performance going to be, and where can I tune it, or where can I use it without a tuner that it's going to work successfully and send most of the energy out instead of having it all reflect back? And so it's hard to see in this picture. Some of the others will be a little bit better, but we've got more of an infinite SWR up here, and as we get closer to this particular frequency, the SWR comes down. And this is something that you can tune in this range of 10 or less, and maybe even higher, and have a fairly effective antenna. But then as you go past this particular frequency of interest here, somewhere, I don't know if that's 30, whoops, if that's, if this is 30 up there and this is 3, then half of 30 is what, 15, I don't know, somewhere in here, and then, so this is probably, I don't know.
That's 40.
That's 7 meg, okay. All right, so then as you get past 40 meters and you come up here, now you got a bad SWR again, but a lot of times these resonant things will resonate on the odd multiple, right? So you get multiple bands in the same antenna. And so now we have a good SWR here, and not so bad. We can probably still tune this. It's under 10. And then I think there's another one over here around 10 meters. So this is what we're looking for. And if you remember, I showed you this antenna. They had like 4-band trap antennas or 5-band trap antennas. If you pick the values of C and L right for your traps, you'll get more than just the effectiveness of what that one trap is saying. You actually get other frequencies that are related to those values. I don't want to go into the details right now, but trust me, it works. So when you look at the values on these antenna patterns, you'll see that they're referenced to dBi, which is the isotropic radiator. And basically, we used to always reference our antennas to, I think, just a dipole in free space. But now they're doing most of them reference to an isotropic radiator. An isotropic radiator is a theoretical thing. It doesn't exist in real life, but it's a point in space that would be radiating that energy out in all directions. And so when we're looking at the performance of an antenna, we're usually looking at gain performance, and we usually want to have gain because we're forcing the same amount of energy that might go everywhere, we're forcing it to go more in one direction so we get better performance, better use of that same amount of energy. So we look at that magnitude versus the isotropic radiator, and then we can see, okay, we've been able to make this antenna give us a gain in this direction with respect to if we just left it all go out equally. Does that kind of make sense? So that's what this is talking about here. And so you'll see these different plots that'll show you those patterns. So if you're looking at this one here, if your antenna was going along this axis here, you would expect to see a donut coming out and then back in and going around like this. We'll see that. We'll see this in 3D in a minute. But that's what you expect if you have a vertical antenna. You expect to see energy going on like this, but not as much straight up and not as much straight down. Okay, and if you have a dipole, you expect to see the energy going up this way and this way, but not so much off the ends. And so you'll see these donut-shaped toroidal patterns, like this one. Now, back here. I'm trying to move it. I can't move it until I get into the program. But that's showing the far field pattern. So now if we take a look at it in 3D, we're seeing what's the shape and relatively how much energy is going in this direction, how much energy is going in this direction in the 3D sense. That gives us a better visual understanding of how it's performing the way we want it to go. So again, here's just some verbiage about the dipole. We don't have to go into that. This has been one of my favorite antennas. It's just the inverted V because you get a little bit more omnidirectivity out of it, more omnidirectional. And you know, if you're a poor person with can only put up one antenna, you know, at 25 or 30 feet from your driveway, so it's like 10, 12 feet above your roof. You want to get as much out of the antenna and work as many people in all the directions that you can. So inverted V's tend to be a little more omnidirectional than a pure dipole. Plus, it's easier for us to get those ends supported if we bring them down to where we can get to them. But not too close to the ground because you don't want people to come along and get zapped. Right? Okay, so this shows you the 3D one again down in the lower left corner, and it shows you the elevation plot for the same 3D presentation up in the upper right corner. So if you slice, you see this red line going through here. That's just a slice right down through that 3D shape, and that's what we're showing you up here. So you can actually see this move on the thing and see it move over here too at the same time when you're looking at your antenna performance. Get a feel of where it is. This, like I told you, that the current, this is your current density here, or your current magnitude. So if your current's maximum at the feed point, the center feed point, and you see the current go down to the end. So it'll show you, and sometimes you have more than one element on there, it'll show you the different current distributions on all the elements. There's another one, I'm not sure why. And this particular one is only cut for one frequency, there's no traps, so it's going to be resonant only at one place, or maybe odd multiples of that if we could go far enough up in frequency. But just showing us from 3 to 30, we've probably got 14 meg, yeah, there it is, 14.25 meg on this particular antenna. And on the program, you can actually click on here or hover over it and see the length of each element. Pretty cool. So this is showing several other types of examples. We saw the delta earlier. We saw a dipole, and of course you've got the Yagi. And Yagis are really easy to build if you've got the space and and they're not. I mean, if you get like a log periodic array, I don't know how to calculate those. I'd have to get it out of a book or something, right? But these are more simple. They typically feed at the center. You see this circle? That shows the place that we're feeding it in the program, right? In the center. So this is the driven element because that's where we're putting the energy into. This is the reflector because it bounces off of here and goes that way. So we make this a little bit bigger, and that makes the energy focus in that direction. And we make this one a little bit smaller than the driven element, and that's what gives us our directivity on a Yagi. So you can make a 2-element Yagi, you can make a 3-element Yagi or more. Typically your director is going to be 5% longer, which is easy to calculate, and your reflector is going to be 5% longer, and your director is going to be 5% shorter. And then your distance between is going to be like about 0.28, a little bit less than a third of the wavelength. So and you can see all that in the book somewhere. I love this antenna because many of us don't have the space. So I've modeled this antenna, we can look at it. I use this antenna with those traps on it. I think I take that back. I used just an inverted V with the traps in it and did very well. But I wanted to have a longer antenna, which I used as a doublet, and I didn't put the traps in there. So but my trees weren't in the right place. Even though I had a small city lot with 13 trees on it, your trees are not in the right place. So what you do is you run as far as you can, and then you run the rest of it down here. Basically, what you want to do is have this length be the length of the dipole of interest. And so you say, well, it turns back on itself a little bit. Yes, it does. But you'll find out with antenna modeling that it really doesn't affect the performance that much, because most of your current is in the middle part. So this part doesn't affect it much. You'll see a little bit of skewing of the azimuth pattern. In other words, the directions along the ground. You'll see a little bit of skewing there. And most of these, the way we run them, we're so close to the Earth that when we run them, especially on the lower frequencies, we're nowhere near a wavelength above Earth. So we're going to end up with something that's throwing a lot of energy up in the air and is kind of omnidirectional anyway. And it works out for most of us to have a lot of fun in the hobby. This particular one shows two different resonances here. Well, this one here that they're giving you the data for is where we've selected our cursor. We can go any point in there and look at this, and these values will come up. But this one is at 21.25, which is 15 meters. And this one down here looks like it's 7, or somewhere in there, huh? Anyway, and you can see the slight skewing of that pattern. So when you see the 3D of the model of the dipole that's too close to the Earth for those frequencies, it'll tend to be fairly round or a little bit elongated. Not too much. It's still pretty round because you're getting a lot of energy in all the directions. And you'll see that instead of a regular dipole that's not a Z shape, instead of being along this azimuth, it will be right along here. So what we've seen is it's skewed it just a little bit. But for most of our purposes, who cares? And the elevation patterns are still pretty close in this case on the lower frequencies to that of what they call a Nevis antenna, or a near vertical incident skywave antenna. Throws up a lot of energy up, almost straight up, and you get really good coverage for 300 or 400 miles. And you know, a lot of us in emergency communications, that's all we need, right? This delta seems to have a fairly similar pattern, but just stuff. So that's basically how that works. Now I'm going to open up the program. And I already have it running here. So this is a plain dipole. It's cut for 138 feet, which is really, that's really a 80 meter dipole. And running it at 7 megahertz. So remember we said we're describing the antenna in free space over X, Y, and Z, because that gives us a solid space to work in. And we do have to describe it in a solid space. When we run the SWR, we can see that this one has a nice frequency way over here at somewhere between 7.1 and 7 is where its actual resonant point is there. And we actually have a tunable range from 7 to 7.8 to 8. We can tune over that whole range from 6 to 8 megahertz because it's, you know, basically around 10. So you could actually workstations and not ruin your radio if you have a good tuner. But you really want to obviously be in here, and for the actual band itself, going from 7 megahertz to 7.3 megahertz, we are all under 3 on the SWR. And we're pretty close to 1.5 probably at the actual resonant point. So they're very, very effective antennas for our hobbies. So when you describe this, once you've got that, you can take a good look at it, move it around, you know, real time, see how it looks, especially if you have a lot of different things. If we were to expand that all the way up there, you'll see these little green dots. Those are the ends of the segments. Remember we said we're going to break it up into segments. We're going to solve the equation, the NEC, numerical electromagnetic code equations at those places, and figure out the fields and then add all the fields together. And And we're going to describe things like the feed point, whatever. So this is telling me that I have the length of this wire is 66.8 feet, and the segment length is 6.07273 feet. So, and it's not telling me the elevation, but it's telling me the wire end. Okay? Anyway, so we'll drop this back down to size, and let's go look at some other things we can see. We can look at the actual wire descriptions themselves. So this is the description of the wire, and this one has one wire. It's split up into 11 segments. We saw those green dots. Split up into 11 segments, so we'll make our calculations in each segment, add them together, and we'll see that it runs from a point in space described as 0x minus 33.4 y and 35 feet in the vertical direction. That's one end of the wire. And the other end of the wire, it has the exact same y coordinate, the exact same z coordinate, but it's oh no, the y coordinate is plus 33.4. So we're at the same space, same height. We're on the same x-axis. We're just at different points on the y-axis. 33 feet here and 33 feet here. So, and more complex ones will obviously do different things there. So let's take a quick look at that, and we'll see that if we look at the far field plot, it calculates it. And if I want to see the 3D, I have to go in here and tell it plot type 3D. Okay. Now there's my current distribution you can see on that antenna. And my far field plot again is looking like this. And I can move it around and get a good feel for how that antenna performs. Now in something like this, it looks like it's pretty simple, but you'll see some other ones, especially at the higher frequencies where the geometries are such that there's actually some space off the ground with respect to the size of the wavelength and some other things. And you'll see multiple lobes. This is one big giant lobe. Well, two lobes, one going plus and one going minus, but they're all into a big fat hot dog shape, okay? But in the other ones, you'll see lots of different lobes. They really calculate these things accurately. So let's take a look at another one. Or I'll look at one more thing. It does describe the source, and the source is described as being on wire number 1, 50% from the end number 1 of wire number 1, and it happens to be segment 6. And it gives you phase and the type. In this particular, it's a voltage type source. So if I go and look at my Z antenna, my backyard Z for 80 meters, giving me a segment warning. One thing about the free version of this program, you're limited to only 20 segments. Being limited to 20 segments, your segments can only be so long, depending on how many different elements you have and all that. So you can have hundreds of segments if you pay for the program. But you can get real good approximations with the demo version. Anyway, let's look at the antenna. So here's my backyard Z. Remember, I had trees out here, so that's as far as I could go, but I wanted to go longer, so I went over towards this tree, and I put an insulator on there, and the rest of the way over to the tree was clothesline or something. Same thing on this side. Now, why do I go this way on one and this way on the other? Because what I want to do is to make it as symmetrical as possible, such that the fields are adding and not subtracting. So, if this one, let's blow this up here. If this one right here is, it's feeding up in the middle right here, okay? And then the minus current goes this way and the plus current goes this way. So I've got the field going this way on segment number 4, or line number 4, and on line number 5 I got the field going that way. So rather than have them turn the other way and have the fields opposing, Now, you may want to design an antenna like that because you want a particular pattern, but I was trying to make it as close to a straight dipole as I could. Now, one of the cases of that is I live in a subdivision that has covenants and restrictions. And if I put antennas up, I've got to hide them in my trees. So I have a 1 acre lot and I'd have to hide them in the trees. I happen to have a very high roof. So I have my antenna over the garage running along the roof peak. And I think I have it here. Well, we don't have time. I'll look for it later. Maybe I can show it to some of you. But what I did was to feed it up the center of the peak. So the garage is about 20 feet tall, the garage ceiling, and then above the garage ceiling, the attic is another 10, 12 feet or something. So I'm up there pretty high, even though I'm near Lake Wells, right? So I'm up there pretty high, and I bring the feet up here and I go to the 2 gables of the garage. So I'm getting close to the house now, but I'm not going out over the kitchen or anything like that. So I'm going this way. Then I go down the gable in opposite directions, and then I come back in opposite directions. It's completely symmetrical. Just like I did with the Z, only I had one more step in there. And it works great. I don't have all the bands I'd like to have right now. I need to go put some traps in there, put some parallel antennas up there, but I work at Navy Marine Corps Mars, and the people tell me that they're so surprised that I'm getting down there with the attic antenna. So let's look at this antenna again. Run a far field plot on that and say it still looks just like a regular dipole, but it's slightly skewed. So if I look at the azimuth slice here and look at the 2D plot at the same time, well, it's pretty hard to see that it's anything more than the same as it would be if it was a dipole. It's so close, hard to see the difference. So don't be afraid when you're putting up an antenna to take advantage of what you have. If you want to run a certain length, it doesn't matter if you make turns. Just don't go back on yourself if you can help it, and try to keep the turns minimized, you know. So there's some other things that we could do. We could go in here and pick, I'm going to wrap it up here in a second, but we could go in here to loads, and then we could define where the loads are at. And we could pick the wire number, how far it is from the end, and then we can pick the type of load. This one has, this one is looking at resistance or okay, load type. Here we go. I want to change it to, well, it is an RLC load type. Oh, there it is. Okay, so now instead of just having R and X, I've got R, L, and C. So now I can take the values of those coils and those capacitors that I made for the trap, according to the book, and plug them in there and see how it's going to perform. If I were to put in, let me do something else first before I do that. So we want to see how this antenna performs. We want to know what the SWR is. So we're going to run an SWR calculation. And we're going to pick the start frequency. So we're going to go here from 3.5 to 14.5 meg, and we're going to go every 0.25 megahertz. We're going to run that. It's making all those calculations every time it stops there. And there it is. Now I happen to have an i5, but it's a 4-year-old i5, but it's a pretty good Pentium. And here's a frequency at resonant point at 4.5 and a resonant point at 13.75. Well, that's not what I want. So I'm going to change my length and fool around with that to adjust it. And that's all part of coming up with your antenna design. So and one other thing is you want to know how to put those loads in. We talked about that. You want to know how to put the source in. There's a place for that. And you want to know how to do your wires. So your wires are again going to give you X, Y, and Z on N1 for wire 1 and X, Y, and Z on N2 for wire 1. And then you'll, if you have multiple wires, you'll run wires connected. And this shows you that N1 of wire 1 is also connected to wire 4 N1. It tells you right there. And the other end of wire 4 must be out in free space because it's not listed here. But it shows you what wire the different ends are connected to it. So that's handy. As you build this in your mind and look at it on the thing, you can keep adjusting it until you get what you want. So that's how it all works. You know, try to put that together with a little bit of theory. And now what I'm happy to do is we can throw together a quick antenna and put the values in there. We can measure it with the antenna analyzer and see if they come up to be the same and just fool around. So download EasyNet demo version 5 and start playing with your antennas. Any questions?
Yeah, when you showed your SWR plot there, it doesn't let you do it backwards and basically say, okay, this is what the plot is right now. And does it let you adjust that so it then changes the values of your links for you?
No.
Oh, okay.
This allows you to, read what it's calculated, but you have to go back to the model and tell the model what you want it to be before you can calculate it.
It's too easy that way, Russ.
Yeah, I was thinking it would be the inverse.
What happens?
Because you calculate wire size and.
Yes, it takes into consideration wire size. If you look at wires here, here's your wire diameter, and you can put it in a value or a wire number, like one number 14, which is one that I use most of the time. But sometimes if I'm using, I had a nice tri-band vertical that I made, and it's easy to mount from the gable of your 2-story house, right? And ran a couple of what do you call them?
Parasite.
No, a couple of
Radios?
yes, a couple of radials, and I had 4 radials, and a couple of them going out to trees, and a couple of them going out to the gutter, along the roof line. And of course, the roof has a slope to it, so they're actually down a little bit, which helps with the pattern. But I had a couple of radios tuned for 14, a couple of them tuned for 10. Now, obviously, I'm going to have a better 14 in one direction, towards the radio, and a better 10 meters in the direction of the 10-meter radios. But trying to get a tri-band vertical to work, you have to have a lot of things going for you. I had traps, I had 2 traps, and I had the radios in order to get it tuned right.
Do you have a name and version of the program you're using?
It's called EasyNet, EasyNEC version 5. That's the demo is version 5. I don't know if he's got what version his newer version is, but I think it's been updated within the last year. And he's been doing this for a long time, so I don't know how much longer he's around, but so I don't remember how old he is. EasyNet demo right there. EasyNEC demo. Other question? Okay, so do I have a volunteer to put this on the screen? Too much to cover in such a short time, but I appreciate the opportunity to share that.